Okay, so we'll continue today from where we stopped in last lecture. In last lecture, we introduced the parallel resistors. We talked about the series resistors and the parallel resistors, and we have shown why the inverse of the equivalent equals to the summation of the inverses. And then we said that this is the equivalent resistance for two resistors that are in parallel. So if you recall, uh, probably we can redo that. So if we have here two resistors that are in parallel, R1 and R2, where this is I2 and this one is I1. If we apply KCL right here at this point, so if we say KCL at A, what do we get? We get I. If we take the entering as positive, then would be I minus I1 minus I2 equals to 0. And then I is I1 plus I2, where I is the voltage divided by the R equivalent. So here is V divided by R equivalent, right? This is the total current I, where this voltage is the same across R1 and R2 as well because they are in parallel. So here I have V as well. Maybe we can make it in different color. So we have here the same voltage across both of them because they are in parallel. So back to here, then I can write I1 as V over R1 and I2 as V over R2 as well. And then if I take V outside, one over R1 plus one over R2, then I can conclude by comparing both sides that 1 over R equivalent equals to 1 over R1 plus 1 over R2. Now we can extend this to n resistors in parallel. So the general equation will be 1 over R equivalent equals to 1 over R1 plus 1 over R2 plus 1 over Rn. So this is the general expression for n resistors that are connected in parallel. It would be easier, as we will see later on, to deal with the conductances than the resistances when they are in parallel. Why? Let's first define the conductance. The conductance G equals to 1 over R. And the unit for the conductance is Siemens. And it defines the opposite, actually, the inverse of the resistor, which means that if the resistance defines the hardness of the charges or of the current to go through the material, then we can say that the conductance defines the easiness of the current or the charges to go through the material. So in this case, if I have a resistance of R equals to 0, which is a short circuit, this basically means that the conductance is 1 over 0. This is infinity. You have an infinite easiness when it comes to the current flow in this branch. Now, if the conductance is the inverse, then it makes sense that the 1 over R equivalent is indeed the G equivalent. And then the inverses for those resistors would be conductance of the first resistor plus the conductance of the second, because conductances are the inverses, and I'm adding here the inverses of all those resistors in parallel. We will see where this can help when it comes to applying the current division. Now, the current division, when it comes to two branches, I can only use two branches if I am to use the resistances. Why? Because I have to make, if I have several branches, I have to combine them into one branch that I'm interested to find the current in, and the remaining branches, I have to find the equivalent for them. So when it comes to the current division for resistors, I can only do it on two branches. And what does the current division say here? If I want to apply the current division and I have those two resistors that are in parallel, well, this one is I1 and this one is I2. Let's assume I want to find I1 using the current division. So again, back to the KCL, I'll take the KCL. So I have, as I have seen earlier, I have the total current I equals to I1 plus I2. So in this case, if I want to find I1, for example, then right now I'm deriving the expression for the current division. So in this case, I1 equals to I minus I2. So I will write I2 now in terms of I. So how do I write I2 in terms of I? At the beginning, I need to find the equivalent resistance. So here, if R equivalent, as we have seen earlier, equals to R1 times R2, and this is only for two branches. I can use this expression only for two branches divided by R1 plus R2. So this is the R equivalent, and then what would be the voltage? The voltage here would be, again, this I, total I times the R equivalent. So I have here V equals to I times R equivalent, right? So this is V, which is I times R1, R2 over R1 plus R2. This is V. Now, if I want to find I2, then I can take this V and divide it by R2. So here I have I2 equals to V divided by R2, and in this case, I2 is I times R1, R2 divided by R1 plus R2 multiplied by 1 over R2. Again, I'm deriving the expression for the current division just to show you where did this expression came from. So here R2 can cancel, and I end up with I2 equals to I times R1 over R1 plus R2. Now, if you take this and substitute it here, you get I1 equals to I minus I R1 over R1 plus R2. Then if you take I outside, then I1 is I, then R1 plus R2 minus R1 is R2 over R1 plus R2. Now notice that I1, the current that goes into R1, is proportional to the ratio of the other branch resistance divided by the summation. So I1 is proportional to the other branch resistance, which is R2, divided by the summation. Which means if I want to find I2, then I2 would be I divided by the other branch resistance, which is R1, divided by the summation. So this is how we got those two expressions for the current division. So proportional to the other branch resistance divided by the summation of the resistances for those two branches, I1 and I2. Now, the resistance, we can only use two branches. Now, the advantage of the conductances that I can use as many branches as I can. And in this case, I will be dealing with I1 as proportional to the conductance of the same branch for the current that I would like to find in. So here, if I have, let's assume here I have three, three resistors, but now I will be using the conductances, which are the inverse actually of those resistors. In this case, if I am interested to find I1, it will be proportional to the conductance of the same branch I'm interested to find the current in. So here I can say I1 is I times G1 divided by G1 plus G2 plus G3. So it's the ratio of the conductance for the branch of the interest divided by the summation of all the other branches. And this is the general expression. However, for the resistances, you have only to combine them in two branches. You can only do it on two branches only. For the conductances, you can do it for as many branches without any simplification as possible.
All right.
Yes.
So you're saying, like, if you had 3 or 4 resistors in parallel, you can't say R equivalent is R1 times R2 times R3 times R4 over R1 plus R2 plus R3 plus R4.
No,
you can't do that with more than 2.
No, you have to use the general expression, which is 1 over R equivalent equals to 1 over R1 plus 1 over R2 plus 1 over R3. Any other questions? Okay. Now let's look at those two special cases where we have two resistors. One of them is a short circuit, the other one is an open circuit. Now we know when it's a short circuit, we know that all the current is going to go through this path. No current is going to go through any other resistors in parallel. So this is to keep in mind. And if you go to the expression that we just derived, let's say I1 equals to I, we said R2, the other resistor, divided by the summation, and I2 is I R1 over R1 plus R2. Now here, if R2 is 0, then I1 is 0. Why? Because all the current is going to go through the zero path resistance. No current is going to go through any other resistors in parallel, and that's why we call the zero resistance that is in this case connected in parallel with R1, we call R1 shortened out. R1 has been shortened out by R2 equals to 0. Now, here, if you look at infinity, which is an open circuit, if R2 is an open circuit, then no current is going to go through R2. And this is here by, if you take R2 as an infinity, you're going to end up with whatever number divided by infinity, and in this case I2 would be 0. If you want to find I1, then here I1 is I R2 over R1 plus R2, and in this case if R2 is infinity, you're going to end up I infinity over infinity, and this equals to I. So all current will go through the resistor R1, and no other current is going to go through the second resistance because it's an open circuit. Okay? Any question? Now let's look at this example here. In this example, we want to simplify those resistors to find the equivalent resistance. So how do we solve this problem? The first thing you need to do is to start from the far end and come back forward toward the input of this circuit, which is those two terminals, if I am to call this one A and B. What does this mean? This means that I have to take it step by simplifying and coming, forward toward A and B. So in this case, the first thing I can see that this resistor and this resistor are connected in series. So the first thing to do is probably is redraw the circuit while simplifying that step. You can also notice that 3 and 6 are in parallel. So you can go 2 and then say this is R equivalent 1, 2, 4, 8, and then simplify this one, call it R equivalent 2, where R equivalent 2 is 1 plus 5 and R equivalent 1 is 6 times 3 divided by 6 plus 3, and we know that those two numbers are always going to give me 2 ohm. So I have this one now as 6, and I have this one as 2. Now the next step is to keep simplifying. I have now this 2 and this 2 are in series. Then this circuit can be simplified further to look like 4, 8, while R equivalent 3 is indeed 2 plus 2, 4 in parallel with 6. So I have 4 times 6 divided by 4 plus 6. And in this case, R equivalent 3 would be 2 point, this is 24 divided by 1.7 ohm, and then the R equivalent, the total is those three resistors are connected in series, so it's going to be 4 plus 8 plus 1.71. R equivalent as 12, 13.71 ohm. Any question about this example? How did we solve for the equivalent resistance? Okay, so we've seen such examples in Physics 1010 before. We're just trying to refresh your memories and warm you up for the next. To we have any time here. So this is 6. This is 2 plus 2, 4. 4 and 6 4 times. Oh, sorry, we have a typo here. 6 divided by 14. It's 6 and 4. Oh, sorry. 4 and 6. Yeah. So it's 2.4 plus 2.4. And this one becomes 14.4 ohm. Okay. Now let's do this example number 7 here. We want to find the equivalent resistance. This one is a bit tricky. However, if you pay attention to how the resistors are connected, it should be easy to solve it. The most important thing is to keep in mind the definition of the node. If you understand the definition of the node, then things would be way easier to solve. So in order to know how is the circuit is connected, we will be using the colors here to show us which nodes are connected, which are the one nodes. I can define the terminals that are connected to one node. So let me do this here. So those in red are are one node, and those in blue are one node. So you can see that the resistor 12 and the resistor 4, both of them are connected to the red and the blue. What does this mean? This means although we're seeing here a cross, but this cross basically doesn't make anything, but this 12 ohm resistor is indeed connected with the 4 ohm. So let me do the other node here in different color. All resistors that are having both same colors are connected in parallel. So let's look at the resistors that are connected to the blue and red and circle them. I have the 4 ohm connected between red and the blue. I have the 12 ohm connected between the red, so the red and the blue. What else? Look at the 6 and the 3. They're both connected to the same colors. 6 and the 3, they're connected to the green and connected to the blue. What does this mean? This means that 3 and 6 are in parallel and 4 and 12 are in parallel. So I can redraw now the circuit as the following. 3, 6, 1. Then I have the 12 and the 4. So this is the 4. And the 12. Then 1 and 5. Right? Now the problem seems to be straightforward after I did what I've done. Now I have 1 and 5 in series, and then this 6 is in parallel with 4, in parallel with 12, and then so this one's 6, 4, and 12. 3 and 6. Okay, so now what I can do, I can find the R equivalent for those three that are in parallel. So I have here let me call this one R equivalent 1. So 1 over R equivalent 1 as 1 over 12 plus 1 over 4 plus 1 over 6. Then so 1 over R equivalent 1 is 0.5, and then R equivalent 1 becomes 2 ohm. So this is 2, and then this can be now simplified into 6, 3, 10. So now we have 1 and 2 that are in series. Equivalent is a 3. Then this is 3 with the 6 and the 3 are in parallel. 3 and the 3 is 1.5. Any two equal resistors that are in parallel, the equivalent would be half the resistance. So I have here 3 and I have here 3. It's going to give me 1.5, and then 1.5 in parallel with 6. It will be 1.2. So here are equivalent 2, which is basically now this whole thing, but taking 3 and 3 first will give me is 1.5. Then I have 1.5 times 6 divided by 1.5 plus 6, and R equivalent 2 as 1.2 ohm. Then I have now the R equivalent as this 1.2 ohm plus 10, then R equivalent as 11.2 ohms. Any question about how did we solve this problem? No questions? Okay. Now let's move on to the transformation. All what we have done so far was simplifying some circuits that are made of series and parallel resistors. We had resistors that are connected in parallel and series, but what would we do with circuits that have resistors that are neither connected in parallel nor in series? In this case, this is an example for here. In this case, we have those resistors. If we try to do the coloring, the same thing we did for the previous circuits. So this is a node. This is a node. And this one also a third node. So if you look at this circuit, you would notice that you don't have two resistors that are connected in series. You cannot see one single current that is the same in two resistors. And also, you will not be able to find two resistors that are sharing the same colors when it comes to its terminals. So none of those resistors are connected in series with any. None of those resistors are connected in parallel with any. So what would we do in this case? In this case, we have to break the circuit by doing the transformation and changing the topology from one physical topology to another. That's what we call the Wye-Delta transformations. So the Wye-Delta transformations basically take resistors. Yes, yes. So here, for example, if I have resistors connected this way, yes, I call this is a topology that I am calling delta. And then this is a second topology that I am calling Y. So that's a topology. This is how the circuit is being connected. They form some sort of delta connected this way, as you can see. This is what we call delta. Or if they are connected like a Y, or sometimes they call it a star, it's a different topology. Now the transformation, the Wye-Delta transformation, is going to give me an equivalent circuit such that I can replace the one topology with the second one. So I have expressions will allow me to replace this delta topology or delta shape with this Y shape without losing the same performance of my circuit. So it is an equivalent circuit such that I can take one, replace it with the second one without affecting the performance of the circuit. However, the second topology would basically break this no solution and allow me now to do further simplification. So we will see how do we do this. So that shape that looks like a triangle, we called it delta. And remember, those ones are still connected in the circuit, part of the circuit. So how do we do the Wye-Delta transformation? The Wye-Delta transformation is done as the following. If you have if you have a circuit that is made of delta like this, and here let me call this one RA, RB, and RC. The procedure goes as follows. I come here and I draw the Y topology inside. Eventually, I want to replace this delta with this Y. And I come here and I call this one R1, such that if you notice this R1 would be on the other side of RA. right? So this is R1. For RB, I take this resistor. I call this one now R2, and this one is R3. So this is how I have chosen R1, R2, and R3. Okay. And
Sure.
then, yes,
So R1 is equivalent to RA, R2 to RB, and R3 to RC, but they've been rearranged.
the whole circuit is equivalent. You cannot look at one resistor only. The whole circuit, the whole circuit is equivalent. The red one is equivalent to the black one. The black one I'm calling it delta. The red one I'm calling it Y. So eventually, when I remove the delta and I keep the Y, the performance would be the same. This circuit is equivalent to the delta circuit. The Y circuit is equivalent to the delta circuit. The way we calculate the resistors, you will see now. So assume you have RA, RB, and RC. You do have those ones. Those ones are given to you. RA, RB, and RC. They're given to you. You have a circuit that has this delta, and you know the values of those resistors. You need now to replace this delta with its equivalent Y circuit, right? Then this is how you do it. You say R1 equals to R2, R3. Now, when you go from Y, from delta to Y, the denominator here would be the same, which is basically the summation of those delta resistors. So here, RA plus RB plus RC, RA plus RB plus RC, RA plus RB plus RC. Now, what about the numerator? R1 is basically the product in the numerator of the two adjacent resistors, which is this one and this one. So here is RB times RC. What about R2? The adjacent one are RA and RC. So here is RA, RC. What about R3? R3 is RA and RB. By the way, you don't have to memorize. Those ones will be provided to you in the formula sheet. But you have to understand the topology, those topologies. But the equations themselves will be given to you. So R3 is RA times RC. Now notice that the denominator is the same for all of them. So after you do this, then you can delete the delta, and in this case, you have now your new circuit. We're going to see this in an example. We're going to see this in an example. So again, you have here the delta. We're going from delta to Y, from delta to Y. In this case, you have the delta. So those are given to you, RA, RB, and RC. When you draw the Y inside, you pick R1 such that it is looking to RA like this. You pick R2 such that it will be looking to RB, and you pick R3 here such that it is looking to RC. Okay? Why do we do this? In general, you can pick them the way you want if you understand the procedure. But in order to follow the same order of those three equations, you have to pick R1, R2, and R3 this way. However, in general, it doesn't matter. It does not matter as long as you understand that in the numerator, it is the product of the adjacents. If you understand that, then you don't have to follow this order R1, R2, R3 to be picked up this way. Is this clear? So this is the delta to y. Now, what about the y to delta? Let's assume that you have your original circuit is a y topology, is a y configuration, and you want to go to the delta. How do you do this? Y to delta. In this case, if you maintain the same orientation for R1, R2, RB here, and R3, RC, in this case, the, the numerator will be the same for all of them. So it is the opposite. Here, for y to delta, if you're going to delta, the numerator will be the same for all of them. Look at the numerator. It is the product of all the possibilities, right? R1 times R2 plus R2 times R3 plus R3 times R1. This is the same for all of them. Now we're going from Y, we're going to delta. Our original circuit is Y. I need to replace this Y circuit with delta. This is how I do it. I divide by what? So R1, R2, and R3 are given to me. So those ones, R1, R2, and R3 are given. I need to find RA, RB, and RC. So the numerator is the same for all of them. What about the denominator? The denominator is basically for RA, we'll be dividing it by R1. For RB, we'll be dividing it by R2. And for RC, it will be dividing it by R3. Okay? So this is how I go from Y to delta. Again, the orientations of R1, R2, R3, RA, RB, RC. If you want to use those equations as is, then you have to maintain the same orientation for those resistors. You have to pick R1, RA, RB, and RC exactly the same way they've been picked up here. Otherwise, if you understand how to go from delta to y, from y to delta, you don't really need to worry about those equations. You can derive those expressions based on your understanding to the y delta and delta y transformation. Any question about y delta and delta y transformation so far? We will solve an example to show you how those transformations are important and useful in uh, solving or simplifying circuits that have resistors connected in a way that they're neither in series nor in parallel. Okay, so let's do this example. Obtain the equivalent resistance RAB and use it to find the current I. So we need first to find the equivalent resistance. Now, if I look at this circuit and I do the coloring again, coloring is very useful to you at the beginning of solving, circuits, to make things easier for you to know which nodes are connected, which nodes basically, or which components are connected to which nodes. So let me take this. So as you can see, we have four distinguished electrical nodes here, and I can't find two resistors that are sharing the same nodes. So I don't have resistors that are connected in parallel. I don't have resistors that are connected in series. So here we have a delta Y case. So you're saying delta Y case. How does this look at delta? It's not looking at delta to you. Well, if it's not looking at delta to you, then look here. You will see that this topology looks a Y topology, right? So I have Y here, topology, or if I use this 5 with the 12.5 and the 15, I have a Y here. So I have two Ys, right? And how many deltas? If you look at the 10, 30, and 20 carefully, you can see that those are delta. The 10, 30, and 20, they are indeed a delta. If I am to bring this 10 a bit to the right, I can show you that this is a delta, right? And 30, 10, and what about the 20? The 20 is is here. So that's a delta. Where else? I have the 12.5, 5, and 10 as delta as well. If you bring this 10 to the left, the 12.5 to the right, you will see that they make a delta. Same thing here for the 5, 20, and 15. They also make a delta, right? So I have three deltas and two y's. I can pick one of them to start. Now for me,
Sure.
yes, go ahead.
So essentially, a T shape is equivalent to a Y.
That's correct. And we've seen this one here. See that? So this is a T shape that is equivalent to a Y, and this is a pi shape that is also equivalent to a delta. So as long as you understand that this is one node, so either they are physically touching or they are not touching apart like this, they belong to the same node, electrical node, right? We have agreed upon that the electrical node is basically defined by a net of wires that are probably connecting several terminals of several devices. So this construct a node, and that's why here when we colored those wires, we treated this net of wires that are connecting those components as a distinguished electrical node. So keep this in mind. This is extremely important to understand the definition of the electrical node that we are using in this course. Any other questions? Okay, so we have here, as I said, we have three deltas and we have two y's to pick from. Now, for me, I will solve it in two ways just to show you. Let me start first with y to delta. So I will pick this y, the 10, 20, and 5, and convert it into a delta. So in order to do this, I will redraw my circuit here with slight modification to make it easier for me. You don't have to do that, but as long as you're doing it for the first time, probably it's worth doing it as long as you understand how to do it. So what I'm going to do, I'm going to tilt this one a bit just to make it look like a Y to me. So when I put my delta would look easier. See what I did? I tilted this point to make it look like more. So this is 10, this is 20, this is 5, this is 12.5, this is 15, and then I have the quarter source here, 120 volt. And this one is 30. So if I want to draw the delta, my delta is going to look like the following. I have one resistor here. I have a second resistor here, and I have third resistor here. Again, as I said, is as long as you understand how to. So let me call this one R1, R2, R3. If you want, I can call this one RA, RB, RA, RB, and RC, just to maintain the same notations for the delta and the star. Okay, so now I want to go from Y to delta, from Y to delta. If you recall, this was based on the equations that I have introduced. This one would be R1, right? And this one would be R2, and this one would be R3. If you want to use the equations that we provided right away, then you can now, you know which is which. You can say RA equals, based on, put that equation, substitute R1, R2, and R3, and find RA. For me, it doesn't matter. I can do it either way. So if I want to find RA, and if you recall, we said when we go from Y to delta, the numerator is the same for all of them. So it will be 5 times 10 plus 10 times 20 plus 20 times 5. Dividing it by 20. What about RB? RB is the same. So here I have 50 plus 200 plus 100 as 350 divided by 20. Sorry, RB is not 20. This one is RA is 350 divided by 20. RB as divided by 10. 35 ohm. So I have here 35 divided by 17.5 ohm. And I have RC equals 350 because it's the same numerator divided by RC is 5. Then RC is 70 ohm. Okay. Now, if I come here, mhm, here, and now I remove now those. I said RA is 17.5, RB is 35, RA, 5 ohm, and RC is 70 ohm. Now, if you look now at this circuit, I have RC and 30. They are in parallel, right? So now this circuit can be simplified. What else? I have a 12.5 and the RA are also in parallel. Look at again, look at the nodes, right? They're sharing they're sharing the same node, 12.5 and RA, both of them. They are in parallel. RC and 30, they are in parallel. RB and 15, they are in parallel. So now I can redraw the circuit to look like the following. I have a 12.5 in parallel with RA, right? And we have 15 in parallel with RB. And then we have RC and 30 are in parallel. So in this case, I can simplify the circuit to be the following. I'll call this one R equivalent 3. I'll call this one R equivalent 1. And this one R equivalent 2. So here is R equivalent 1, R equivalent 2, and this one is R equivalent 3. So here you have RC and 30 times 70 divided by 30 plus 70 is 21. R equivalent 1 is 12.5 in parallel with RA, so 12.5 and 17.5. So let me do this one here. So R equivalent 3 is 70, 30 over 70 plus 30. R equivalent 2 is 15 times 35 over 15 plus 35. And I have R equivalent 3 as, sorry, R equivalent 1 as 12.5 times 17.5 divided by 12.5 plus 17.5. So R equivalent 1 is 12.5 times 17.5 is 7.29. R equivalent 2, 15 times 35 is 10.5. Then R equivalent total is 10.5 and 7.29 are in series. So you have 17.8 times 21 over 17.8 plus 21. So R equivalent is 9.63 ohm. And in this case, we have that this one is 120 volt, then the current I is 120 divided by 9.63, and the current is 12.46 ampere. Okay, so this is how we solve the y to delta, and you can try yourself by solving it from delta to y. I can tell you now, if you take delta to y, if you take this one, if you take this delta and convert it to y, you will find that you will probably need to do one more simplification going to y again. So some of them will require more than one transformation. Some of them will require one transformation. Now you here, when I took this circuit that's right in the in the center of my whole circuit and convert it to delta, I managed to simplify it because it will be simplify both sides of the circuit. But if you take the delta, for example, this one, and go to y, you will find out that you will need one more simplifications. So here in our case, because we took this y that is in the center of the circuit, we managed to simplify it and find the equivalent resistance in only one transformation. But don't be surprised if you notice that you may need more than one transformation to simplify. Any questions so far? Okay, so last slide I want to talk about is the, yeah. Yes, those are PowerPoint. I usually upload the PDF version. Why, do you need the PowerPoint? No problem. I can do this. You will. Okay, so the last slide I want to talk about is the ideal meters. We're not going to go through uh, the meter, the same material that is in the textbook. We're only going to look at ideal meters. We're going to be using ideal meters. In this case, we have two meters that we're interested to use in our circuits. One of them is the ammeter that basically measures the current, and the voltmeter that measures the voltage. So the ammeter, we have it in series. So if we have a circuit, if we have a circuit, okay. So if we have a circuit here, I have to break this circuit to insert the ammeter. Now look at this ammeter here in this case. I have to break the circuit and insert the ammeter in series. Whenever I want to measure the current, I have to break that branch and put my ammeter. Now the ideal ammeter will have zero resistance, such that here it does not withdraw any power from my circuit. So here I can look at this one as has a zero resistance that does not withdraw any current. Now for the voltmeter, as you can see, this voltmeter will have an infinite resistance such that the current withdrawn from my circuit is zero. So my voltmeter does not withdraw any current from my circuit. So whenever I see a voltmeter that is connected with any component here in parallel, always keep in mind that the current withdrawn by this voltmeter is zero. Why? Because it has an infinite resistance. However, the ammeter has a zero resistance such that it does not withdraw any power from my circuit. So this is what I want to talk about when it comes to using some of the ammeters or voltmeters in our circuits. Those are our ideal instrumentations. Any question about what we have covered today? This concludes our lecture for today. If you have a question, please go ahead.
I have several, sir.
Okay, go ahead.
Is it possible to like treat a Y shape as though it were two resistors in parallel that converge and then go to a resistor in series?
No, we cannot do that because at the end, the Y is still connected with other components. So we don't have a Y as a standalone Y. It's not a Y like this by itself. No, this has been cut out from the main circuit. So what I am doing, I am only replacing. So if you imagine that you cut it from those points A, B, and C, what you're doing is only replacing those ones with a delta at the same points.
Okay.
So this is still connected to the same circuitry.
Sorry, I wish I could annotate here and make it help me explain this. So if I had, okay, I think I'd have to shoot you an email for this because
No,
I'd
no,
have to
yeah,
draw.
yeah, no problem, no problem. Feel free to send me whatever emails that you want. I think I can. Just a second. Let me see here.
So you can't say a resistor like this. Well, sorry, a Y like this is not equivalent to saying this. These are not equivalent.
No, 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 Matthias, because as I said, your Y here is not a, this is not the circuit by itself. This is has been cut from a bigger circuit. So you have currents coming and going, in that part of the circuit. You cannot say that this is your circuit by itself. You can't. You can't. Those are different nodes. This node is different than this one, is different than this one. So look at this circuit. Otherwise, if we can simplify it this way, then we don't need the transformation. Is that clear?
Yes. And for the last problem, did you get R equivalent as 9.63 ohms? For the last example we did.
9.63. That's correct.
All right. All right. Well, take care then.
You too. Thank you so much. And I'll see you on Thursday. Have a good day.